Okay, this is going to be the third part of the Chapter 7, 8, 9, Unit 2 AP Statistics lessons. So we'll pick up where we left off here. I'll share my screen again. All right. And let's see. So next we're going to talk a little bit. We've talked about fitting an LSRL to data, the general shape and description of associations. Explanatory versus response variable. We talked about correlation coefficient and how to generate and use the LSRL, the line that fits the data. It turns out that that correlation coefficient R, if you square it and get a positive value, that value also has a meaning. So we're going to talk about that next. So R squared, which is just correlation coefficient squared, is called the coefficient of determination, okay? And it's a measure basically at how good the model, the LSRL model, is at explaining the variation in the y's as x varies. So you can think of it, it's valid to think of it as what percentage of the variation in the y is being explained by the model that connects the y to the x, okay? So I'm going to try to show you sort of an intuitive explanation, and then I'll show you like a specific thing. And I'm going to go back to this thing that I showed before, which is on an online thing. So let's say we had some data values here, these 1, 2, 3, 4, 5 data points, okay? And at first, I don't know anything about the data. So if I had no way to fit a line to that, I would just say, well, x is varying and y is varying. And I could at least figure out where the average of the x's and the average of the y's are. That's the centroid right there, okay? And so I could just say, well, if there's no association between this data, then I could just draw my LSRL to be horizontal. And if I did that, we're saying there's no association. So this variation of the y, we can't do anything to predict it, okay? And if I wanted a measurement of how widely dispersed this y was, I could calculate the sum of the square of the residuals to just say how bad is the model if I just assume there's no model to be had. And so if you just take the sum of the squares, maybe we get some number here like 25.3. That's the sum of the squares, okay? But then if I did instead fit the model, right, then that means that actually I can make a line that does a better job than that, right? So that error was 25, right? And if instead I change it so that the sum, I fit a better model to that, now the residual in the error is 18. The sum of the squares is 18, so there's less error, right? And that means that the difference is the amount of the error that is being removed by fitting the correct model to the equation, right? So that's the percent. So if you think of it as like this 18 out of the 25, that's the percent of the error that's still left, even if I fit my best model. Then the other 100% minus that percentage is the amount of the variation in the y that is successfully being modeled and predicted by the model. So I don't know if that helps to see it, but so if there was no association, we would have some sort of error here. Maybe we get, like in this case when I did it, 16.65, right? But when I reduce the error, when I fit the line, the error goes down, right? So that error that's left is, say, 63% of the variation that no matter what I did with the model, I can't get rid of it. It's just normal variation that's going to happen in data, right? But that means that the difference, the other 37%, was explained by the model that relates it to x, okay? So let me show you how we would specifically get this, okay? Let's actually use our data, okay? So I'm going to use the data from the values that we have in there. And I still have my data in list 1 here for list 1 and list 2 for the height and step data. So let me run the linear regression again. So I know if I go, let me go back to the command line. If I go stat over here, and then I go down to 8, and I run linear regression on list 1 and list 2. Okay, and I want to show you something else too before I go further here. Okay, so I get my R value. My R value was negative 0.873. So R squared is literally that number squared, okay, which turns out to be 763, and the calculator does that for us, right? So what that's saying is that this model is predicting about correctly predicting about 76% of the variation. Now, what was this model again? This model was that we could predict the number of steps people would take from their heights, right? And we had some sort of a scatter plot that looked like this, and when I drew a line through the data, okay, it didn't perfectly fit, right? That's why the correlation is not exactly -1, okay? But now we can think of it this way. Think about all the things that might affect the number of steps that we take, right? I'm going to list some things here. Usually in class we would have people call out things that they think might affect. So height is one, right? That's one thing. But there's other things, like maybe their length of their legs, right? Maybe some people are, it might be the same height, but some people, but you know, two people have the same height, but they have different leg length, right? So that might, or maybe their level of energy, right? If they're really low energy, they might take small steps, whereas if they're really energetic, they take, you know, large steps, right? So there's a lot of different things that could affect number of steps, right? So if I look at what causes variation, now I have variation, right? In fact, let me mark it over here, right? There's variation in the Y, right? Variation in the number of steps, okay? So there's variation in here from person to person, right? And we're saying all these factors might be causing that variation. What we just found out from finding R squared is 76.3% is that about 76% of this variation seems to be connected and predictable from the height. And that means that the remaining, what is that, 28%? The remaining 28% of variation, that's due to some other stuff like leg lengths, energy level, or something else. So that's the meaning of the coefficient of determination. And sometimes we're asked to explain it. So we might say something like, there is actually kind of a standardized way to state that. Let me just state exactly right now how we would state that. The standard way that we would explain it is we would say, if R is 0.76, we would say about 76% of the variation in number of steps taken is explained by the LSRL model, which relates number of steps to height, right? We'd like to say, you know, 76% of the variation in steps is due to height, right? But that's a little too strong. It's explained by the model, which is modeling a connection between the two. So this wording here is our kind of standard wording for explaining R squared, the coefficient of determination. All right. So the next thing I want to talk to you about is something called a residual plot. So a residual plot is just a plot of the residuals, and you can sort of think of it this way. So in your practice packet, I have a place for you to do one of these by hand, because I have found over the years that if you do one by hand, then it really helps you to see what's going on. Okay, so here's the way a residual plot looks. So let's take a set of data that's pretty linear here, like this. Okay, actually, let's start with this one on the right, the one that's not linear. This data is definitely curved. What would the residual plot look like? Well, we're going to plot the residuals. And remember, the residuals are the difference between the actual Y and then the predicted Y. So if you just draw a line from a data point back up, straight up and down to where it connects on the LSRL line like that, right? These little red lines here are the residuals. So here's the way you do a residuals plot. You find the one that's largest, and you make that full scale. So whatever full scale is, right here at this X, we're basically, this is X, and we're plotting the residual on this axis. So this is going to have a negative residual. I'm going to make that full scale here. So I'll put a dot down here that's full scale. Okay, this one is a positive residual, but it's only about 1/3 as high as that. So instead of going, I'll go to that X location, but I'll only go 1/3 of the way out. Okay. And then this one goes almost as high as this one is negative, except in the positive direction. And this one's maybe half as high. So at this X, we go halfway. This has a residual of 0. It's right on the line. And then this is negative, maybe 2/3 of the way down. Okay. So this is called a residual plot for this data. And you kind of see what it is. It's kind of like just taking the LSRL and just moving it down horizontal and just shifting these things up so that we can see the vertical heights plotted against the LSRL. Okay. All right, so that's a residual plot. Let's do one for data that is nice and linear. Okay, this is a good linear association. So we're going to do the same thing. We're going to try to draw in the little residual lines here. Okay, and then I'm going to take the one that's biggest, which looks to me to be this one, and I'm going to make that full scale. So at this X, I'm going to put a dot here at full scale. Okay, then I'm going to say this one's about the same except in the negative direction, so full scale. This one's right on the line here at this X. This one is a little lower, maybe 2/3 of the way down. This one's maybe 1/3 of the way up or less. This one is just a tiny bit negative like that. Okay. So what I want you to notice is that over here, there's basically no pattern. I can't really see a pattern, but over here, I can see a curved pattern, right? So what a residuals plot does is it blows up the residuals so that it's easier to see if there's a curved pattern or if there's no pattern. And when we have no pattern in the residuals, by looking at the residuals plot, that means that the association is linear. Okay, if we have a curved pattern, it means it's not appropriate to fit an LSRL to that data because the data is curved. And we would have to do something to straighten the data. That's what we're going to talk about in chapter 10. There is a way. What we do is we don't fit a curve to the data. We transform the X and Y axes to straighten the data, and then we fit a line to that. We'll save that for chapter 10. Okay, so I wanted you to do one residual plot by hand so you could see what they're like. But then I'm going to show you the steps to have your calculator do that. Okay, so if you have data, I'm going to use the step data and height data in list 1 and list 2. You have to run a linear regression. Okay, so you have to so the first thing you do is you always run a linear regression. Okay, and what that does is it fills up a hidden array inside your calculator called residuals that stores all the individual residuals for each data. So then you go back to second y equals like you're going to do a scatter plot. You set it up to be a scatter plot. And you still have, usually we use the X's in list 1, but instead of plotting the Y's for list 2, we're going to use the residuals. So instead of L1 here, we have to put that we want it to use the residuals array. Okay, so here's where we find that. You see where it says in colored letters above stat, the list? So if we hit the second button and then stat, we get to the list of lists. And if we have recently run linear regression, at the bottom of that list will be a selection RESID, which is the residuals array. So we enter that to put that in there. And then we display the scatter plot, but now it's displaying a residuals plot. So this residuals plot looks pretty good, right? I don't really see any real pattern here. It looks like random scatter. And so this residuals plot indicates that the data is fairly linear, and it's okay to run linear regression on that. Okay? So that's how we run that in a calculator, and the steps are in the notes. All right, so if you have a scatter plot, right, that looks like this, right, the corresponding residuals plot will look like this, right? But if I have some sort of pattern in the data where it's not randomly scattered around the LSRL, like I see a pattern here, you're going to see that pattern magnified in the residual plot. What you're looking for is curves, right? Things that are distinct curves are the things that it doesn't have to be a perfect curve, but if you see something suggesting a curve, this is not enough, right? I do see a slight bit of curving here, but not enough. There's plenty of scatter, I would say linear model appropriate here. So the residual plot is used to determine if data is linear, which means it's allowed for us to do linear regression to fit an LSRL model to it. Okay, so a couple notes about residual plots. The slope of the LSRL is always 0. The LSRL always ends up horizontal. The mean of all the residuals is also always 0. And it actually turns out that you can also find something called S, which is the standard deviation of the residuals. And that's just a measure of how widely dispersed this is. So if S is higher, it means there's more spread around the LSRL, which is associated with the correlation coefficient getting closer to 0. R is getting closer to 0, right? Because if you have higher standard deviation, you're not as closely tied to the LSRL. Okay, before we do the next thing, I want to show you one more thing in the calculator that I just haven't yet. Let me go back to the scatter plot, the scatter plot. Let's go back into our scatter plot. And let me set that back to be L2, which means we'll be displaying on the x's on the x and the y data on the y. Let's just look at that that LSRL again. So zoom 9. There's the not the LSRL. This is the scatter plot of the data. Sometimes it's nice. You don't always have to do this, but occasionally it's nice to have the calculator calculate the LSRL and enter it in on the data plot. Now, what you could do is run linear regression, go in here to y equals and type it in. And if you type the equation of a line in here, then it will display over the top of the scatter plot so you can see it. But there's a clever trick we can use to force the calculator to put that equation into y1 for us automatically. And it's when we run a linear regression. So if you run your linear regression, right, you do specify where your lists are. See where it says store regression EQ? That's allowing us a place to store the regression equation. And so we want to set this to y1 if for some reason we want to see the LSRL on the same plot. There's a couple ways to get this. The fastest way, if you have a TI-84, is to hit the alpha key and then the trace button, and then you can select y1 from that and hit enter, right? But older TI-84s and TI-83s, we have to use a different procedure, and that is that you see where it says variables? The same place we went for normal CDF, but without pressing the color button. If you click variables, and then you scroll over here to y variables, and then you go into the function variables, we can find y1 there, and then we enter it. Now, when we do the calculation, it does the LSRL, nothing changes here. But what happens is this equation gets automatically entered with all the stuff not rounded into y1. And now when we display the scatter plot, zoom 9, we see the scatter plot, but it also draws in the LSRL line for us, okay? So another kind of neat feature, so that we don't have to try to enter that equation by hand if we want to see it. All right, this is a lot going on in this part, so I think just one more thing before we want to stop for the day. Okay, so turns out there are 3 ways to find the equation of an LSRL. One way is to enter data into a calculator, okay? And if you do that, we know how to do that by running linear regression. Sometimes we don't have the data set, but someone has already run the data through a software program that can do linear regression. And then they give you what's called software output, which is a big table of data that looks like this. And it's complicated looking, and we're going to have to wait till next semester to talk about what all this stuff is. But there's a few things we can focus on, right? The first thing is that there's always a part in here somewhere where you have a variable column and a coefficients column. Okay, and one of the variables will be labeled the name of the x variable. Okay, so just looking at this software output, this says that the x variable was time. So what this is saying is the x variable was time. And up here it says the dependent variable was concentration. So this was concentration. Maybe this was like the concentration of drug in the bloodstream after a certain amount of time or something like that. I don't know what it is. Maybe it's the concentration of acid as you dilute it with water over time or something like that. Okay, so what this is telling me is that the coefficient for the time variable is -5.96, and the coefficient for the constant variable is 40.3. Okay, so in such a table like this, everything about this row has to do with the y-intercept term, A. And everything about this row has to do with the x variable term, which is the slope, right? So that's basically telling me that y hat equals A, which is the coefficient for the constant term, 40.3266, and then plus the slope, which is the coefficient for the time variable. So I'd say minus 5.95956x, where x is time and y is concentration, right? So you can recreate the LSRL from their output, so you don't have to run the data, right? They didn't give us the data. So this is how you write an LSRL from software output. The other thing that sometimes we need is R and R squared. So somewhere it'll tell you what R squared is. That's telling me that R squared is 0.908, okay? There's always an adjusted version. We never use the adjusted version in this course, so always the regular version. And then since we have r squared, we know we can find r. R is just plus or minus the square root of 0.908, right? So if you were to take a calculator and take the square root of 0.908, you'll get r is plus or minus 0.9529, okay? And how do we determine the r? Well, the sign of r always matches the sign of the slope, right? Positive correlation for positive slope. So since this slope here, in fact, let me label something here. This number here is always a, and this number over here is always b. Since b is negative, it means we have to choose the negative version. So we know the slope is negative 0.9, or the correlation coefficient is negative 0.9529. So from this table, we can get the full LSRL and r squared and r without having to plug any data in at all. So sometimes this is done so that you don't have to spend a lot of time plugging data in. They'll just give you the analysis that someone else did. All right. Okay. And that's just what we just talked about. All right. This point, we would typically go ahead and do problems 11 through 16. Let me take a quick look at those. Yeah. So pause the video, and then normally I would have people work in groups on this. Try problems 11, 12, 13, 14, 15, and 16. And then unpause it, and I'm going to go over it now. Okay, so let's look at these next problems. Number 11 is this. Okay, it says Alana's favorite exercise machine is a stair climber. On the random setting, it changes speeds at regular intervals, so the total number of simulated floors she climbs varies from session to session. She also exercises for different lengths of time each session. She decides to explore the relationship between the number of minutes she worked out on the stair climber and the number of floors it tells her that she climbed. She records the minutes of climbing time and the number of floors climbed for 6 different sessions. Computer output and a residual plot are shown. So here's the software output, a little piece of it, and then here's the residuals plot. This is not a scatter plot, it's residuals plot. Okay, so it says, what is the equation of the LSRL label variables? Okay, so looking at this, I know this row here has to do with the y-intercept, and this row always has to do with the slope. So basically, this number here is the A. Let me just write it this way. This is A, and this is B. Always true, right? A is the coefficient for the constant. This will either be labeled constant, or sometimes it's labeled intercept. So I could just write this. It's y hat equals the A, negative 3.822, plus the slope, 5.2150 times x, where x is the number of minutes that she exercised, and y is going to be the, let's see, the number of floors that she climbed effectively. Okay, so that's it. You just need to pull these two numbers from the table and write it and identify the variables. Okay, the next question says, is a line an appropriate model for the data? So we look at the residual plot. This is a residual plot, and looking at these numbers, or these dots, let me make them a little easier to see here. That's a nice residual plot, right? Because there's no curve pattern, right? No pattern, right? So the way we would write this is we would say, yes, a line is appropriate because we have to give a reason why. It says justify, because there is no pattern in the residuals, or residuals plot. Most people just say residuals. Yes, a line is appropriate because there's no pattern in the residuals, but you have to state it's because there's no pattern that we see in that residuals plot. Okay, then it says, interpret the value of the slope of the LSRL. So the slope is this let me write it. The slope is 5.2150. The units of that would be number of floors per number of minutes worked out. Okay, so here's our standard wording. I'm going to type this because there's a lot more writing here. For every 1 additional minute of exercise, the number of floors climbed increases by 5.215 floors on average. Okay, that's the standardized way to interpret the value of a slope in AP statistics. For every 1 unit in X, the Y changes by a certain amount on average, but using the words from the problem. Okay. And then it says interpret the value of R squared. So R squared, well, let's see. R squared is going to be this value, which is 0.989. We're not going to use the adjusted value. And again, we have standardized wording for that. We could say about 99% of the variation in the Y variable, which is number of floors, is explained by the LSRL model, which relates number of floors to minutes of exercise. What we're really saying is just about all of the variation in number of floors can be connected to the number of minutes that we exercise, right? But we can't say it quite that strongly. We want to use a phrasing like this. And then what is the correlation coefficient? So R is just the square root of R squared, but it could be plus or minus. So it's plus or minus the square root of 0.989. So if you take the square root of 0.989, that's plus or minus 0.9945, but because the slope was positive, that means we're going to choose the positive version. So it's positive 0.9945. And this is just a computation, so we just have to state that result. Okay, and then let's see, the last one here is interpret the value of S. Okay, so there's another thing on the software here, this S. Okay, now that S is the standard deviation of the residuals. Okay, so first, S is 2.3472. It's the standard deviation of the residuals, right? So if you think about what it means is we have this positive association. It's really high, right? R value, so that the data is like this, right? This is a plot of number of minutes versus the number of floors, right? Floors predicted from minutes, right? And what we're saying is the standard deviation is 2.3, right? So these, I'm going to exaggerate this a little bit, right? Not all of the floors, all the data values are exactly as predicted. There's a little bit of variation, right? And those residuals are like the little errors. How far away was the real data from what was predicted? This is the standard deviation of all those errors. So we have to have some kind of a way to write that. Let me explore a couple ways we could write it, or at least one good way. So one way to write it would be something like this. This is, okay, you could say S is the standard deviation of the residuals, just to indicate that you know what it is. But in context, you could say the actual number of floors is different from the predicted number of floors for given minutes of exercise. S equals 2.3472 means this difference between actual and predicted number of floors is 2.3472 floors on average. Something like that. Okay? It's the average difference, but it's the average number of floors different between the actual and the predicted number of floors for a given number of minutes. Hard to make it kind of a nice flowing sentence like that. So I find sometimes breaking it into two parts like that and saying, okay, the actual number of floors is different from the predicted number of floors. The standard deviation is the average difference. Okay. All right. So I believe that's where we're going to end part 3. We'll save the rest for the end. So that's the end of this video. One more video to cover this really huge set of notes. Remember, we're covering 3 different chapters though.